Okay, so sorry. Today we're very fortunate to have Angeliki Koutsoukou Argyraki tell us about the new era of formalized mathematics and the Alexandria Project. So please take it away.
Thank you very much. Thank you very much for having me at the Topos Institute Colloquium. So I'm going to present a general discussion on the philosophy and motivation behind the use of proof assistance to formalize mathematics. I'm going to present a discussion on the current state of the art and the potential of the area. So as you probably already know, this area has seen a very big boost recently. It's really flourishing. Lots of new people are joining, lots of mathematicians in addition to computer scientists, as it was until now, and lots of young students as well. So of course, there have been other past related talks on this topic at the Topos Institute Colloquium. There were talks by Kevin Bazar, Jeremy Avigat, and Lawrence Folsom and Johan Kommelin on this topic. So inevitably there will be some overlap, but of course, Kevin, Jeremy, and Johan Kommelin, they talked about lean. That was their focus. I'm going to talk more about some different things as well. And of course, the talk by Lawrence Folsom, my PI, it was about some aspects of the Alexandria Project, but he gave some more technical details about certain of our projects, in particular the ordinal partition formalization project. Well, on the other hand, what I'm going to present to you today is going to be a general overview of our contributions so far within Alexandria by my colleagues and me. So it's not going to be a technical talk today. So starting with a bit of history, if we want to go back to the idea of formalizing mathematics, we can go as back as Leibniz, who proposed the development of a symbolic language that could express any rational thought and a mechanical method to determine its truth. So he suggested that to resolve any dispute, we can just say, let us calculate. Fast forward some years later, Boole is considered the father of propositional logic. He wrote his famous treatise, The Mathematical Analysis of Logic. A bit later, a few decades later, Frege developed an expressive formal language equipped with logical axioms and rules of inference in his Begriffsschrift. Moving on, Whitehead and Russell, the famous logicists, in their legendary work Principia Mathematica, they try to express all mathematical propositions in symbolic logic and solve paradoxes of set theory. This is where they introduced type theory. Hilbert, a formalist, not really a logicist, but a formalist, he had quite similar goals. So the famous Hilbert program suggested that all mathematical statements should be written in a precise formal language and follow from a provably consistent finite system of axioms according to well-defined rules. Of course, we all know that Hilbert's program received quite a significant blow because of Gödel's incompleteness theorems. But of course, this does not prevent us in any way from formalizing mathematics, because even though we cannot formalize all of mathematics in one formal system, we can still, in a single formal system, we can still formalize a lot of it, right, of course. And of course, it is no more of an obstacle comparing to doing mathematics in pen and paper, because even doing mathematics in pen and paper requires the use of underlying axioms in that sense. So this does not prevent us from formalizing mathematics in principle. Now, De Bruyne is considered by many the father of modern proof assistance. He created Automath, a predecessor of modern proof assistance, which is based on type theory. And Van Bentem-Utenink translated Landau's Foundations of Analysis into Automath. That was a very significant first work. That was in the late 70s. Fast forward to the 90s, the famous QED manifesto was a very ambitious proposal for a central computer-based library of all known mathematics, fully formalized and formally verified, meaning automatically checked by computers. This was a very ambitious project at the time. Very soon it was considered abandoned, but was it really abandoned? I don't think so, because today we have modern proof assistants, or also referred to as interactive theorem provers. These are software tools for formal verification, the development of formal proofs by using computer interaction. So we have a variety of proof assistants available based on different logical formalisms. So we have different families of proof assistants. We have a proof assistants based on set theory, like Miser, MetaMath, simple type theory, like the whole family and Isabel. And of course, proof assistants dependent on dependent type theory, like Koch, Agda, Lean, BVS. And there are extensive libraries of formalized mathematics available in all these proof assistants. So the general idea is that a human user writes the proof in a formal language via an interactive interface, and this can be checked by a computer. And very often the intermediate proof steps are given by automation. Now, if you'd like to see a direct comparison with specific examples between these different proof assistants that I mentioned, for example, you can see the webpage maintained by Wittrich, formalizing 100 theorems, which is a list of 100 famous theorems formalized, most of them already formalized in certain of these proof assistants, and you can directly compare and see how the different languages look like. This is a quotation I really like by Barendreich and Wittrich. So they say, this is a quotation from a paper from 2005. We believe that when later generations look back at the development of mathematics, one will recognize 4 important steps. The Egyptian, Babylonian, Chinese phase, in which correct computations were made without proofs. The ancient Greeks with the development of proof. The end of the 19th century, when mathematics became rigorous. And the present, when mathematics, supported by computer, finally becomes fully precise and fully transparent. Of course, now you will reasonably ask me, why formalize mathematics? An obvious first reason, of course, is verification. Mathematicians can be fallible. A famous example is the Fields medalist Vladimir Voivodský. He started working in formalization after discovering errors in his own work. Of course, very often we find little mistakes like corner cases, little details, but more serious mistakes can be found. I have some examples. I can give you some references. A second reason is that by many, this is considered to be the future of reviewing. So it has been imagined that in the future, not in a very distant future, actually, because it's already happening. Along with, when submitting a paper to a journal, the author can also would also submit a formal proof of the result, along with a pen and paper proof, and that would significantly accelerate and help the reviewing process. A third reason is that by preserving mathematical knowledge in big libraries of formalized mathematics, we are creating databases which have an enormous potential, and they have an enormous potential when it comes to creating future AI tools to assist mathematicians in their discovery or invention, whatever you prefer, of new results. So this is not a library in physical paper anymore. It is a library written in code, and code is something you can play with, you can interact with, you can modify, you can preserve, you can recycle, reuse. So it is something more alive compared to a proof written in a piece of paper. A fourth reason is that the process of formalization can offer us deeper understanding and new insights. So even familiar material can be seen in new lights when using new tools. And in addition to that, the high level of detail in which a formalized proof must be written, it actually forces us to think and rethink proofs and definitions. When you want to explain a new definition to a computer, you have to think of it from many different angles to really explain it to the computer, to think what is the best way to write a definition, to write a statement. And that helps you very often with understanding, with deeper understanding of the material. So a fifth reason is that this is a very efficient way of keeping track of all the details of a complicated proof. And this is something Johan Kommelin talked about in detail in his talk at the Topos Institute, I believe last week, right? He gave the example of the very famous liquid tensor experiment. This very important recent work where it was evident that thanks to the proof assistant, it was easier to see how each part of the proof interacted with the other parts. And this is extremely useful when we're talking about very complicated proofs. It's not easy to keep all the details in mind. Or just a more simple example, you can just change a part of the proof, remove a lemma and see where your proof breaks immediately, right? Because the proof assistant will notify you. So a sixth reason is that this could help us develop educational tools for students as well. And last but not least, it is fulfilling and fun. So sometimes it feels like playing a computer game while using a proof assistant to formalize mathematics. Of course, I have a comment on an additional personal motivation myself, because my background, I'm a mathematician myself, I'm not a computer scientist. And my background is in applied proof theory and in proof mining, which involves pen and paper extraction of constructive quantitative information from proofs in the form of computable bounds. And this requires logical analysis of a proof and rewriting it to make the logical form of all the statements involved explicit via revealing the hidden quantifiers in the proof. So as you can imagine already, I believe this provokes the question, because of course, when we have different proofs of the same statement, we get different computational content. And this provokes the question, what is it that makes a good proof after all? So, and there are many possible answers to this question. Is it a shorter proof? Is it a more elegant proof? Is it a simpler proof? Now, Hilbert's 24th problem, we all know the list of 23, the famous 23 problems by Hilbert that he proposed in the year 1900. There was a last 24th problem that was discovered later, and what that problem asked for, it was to find criteria for simplicity of proofs, or to show that certain proofs are similar than any others. Then another possible answer to that question is that in terms of reverse mathematics, a proof in a weaker subsystem of second order arithmetic could be considered better in a sense. Or an interdisciplinary proof, for example, a geometric proof for an algebraic problem, or vice versa, it would be considered to give deeper mathematical insight. So if you have a proof that combines different mathematical disciplines, it is more mathematically deep. It brings us closer to deeper mathematical truths. Another possible answer is that a proof that is easier to reuse may be better, because such a proof could, for example, provide some algorithm or some technique or some intermediate result, some useful technical lemma that can be useful in different contexts as well. Or finally, as you could already guess from the context of what I mentioned before about proof mining, a proof giving better computational content. But then we can in turn ask, what do we mean by better computational content? Is it getting a bound of lower complexities? Is it getting a bound that is more precise numerically? Is it getting a bound that is more elegant in the sense of having fewer parameters, that it looks simpler and nicer in the eye? Of course, I'm hoping that we can get some insights regarding these questions through formalization, because of the high detail in which we examine proofs. So a vision for the future of research mathematics is to create an interactive assistant that would help research mathematicians in the creative work. And that could be achieved by many auxiliary functions, for example, by providing hints like brainstorming, directly interacting with the mathematician working in real time, and giving proof recommendations, counterexamples, proof of auxiliary lemmas, or intermediate steps. It could suggest conjectures. It could provide information on relevant literature results. It could notify you, hey, there is a related work that might be of interest for you. Or it could help with bookkeeping on the proof structure, on the proof calls and details. This is already happening, of course. Many aspects of this functions are supported by proof assistants already. And of course, formally verifying the new results. So the goal is to assist mathematicians, not to replace them. This is our goal. So Timothy Gowers, he describes very vividly in this paper here that I'm referring to. He describes in a very vivid way how a dialogue between a user and a computer would ideally look like in the future, to interactively assist the human mathematician to arrive at conclusions, and sometimes at new conclusions, new results. Of course, the computer would need to have access to an extensive database of mathematical material, which is the reason why it would be useful to have extensive libraries of formalized mathematics available. Now, this is some suggested reading in this area. This is the famous QED manifesto from the 90s that I mentioned. A manifesto by Leslie Lamport on the significance of writing proofs in a sufficiently rigorous way, supported by computers, so as to make sure, so as to set higher standards for rigor, so as to make sure that what we have is correct, so for verification purposes. This essay by Jeremy Avigad for the American Mathematical Society, I believe it's from 2018, The Mechanization of Mathematics, which is a really nice historical overview until today. This article by Kevin Buzzard from the London Mathematical Society, it's from 2019, I believe. This is a much more recent interview article that I wrote, What Can Formal Systems Do for Mathematics? A discussion through the lens of proof assistance. It includes a series of 11 interviews with 11 experts in the area. So it is a discussion. I already mentioned before Vygotsky's motivation to formalize mathematics after discovering mistakes in his own work. This is described in this essay that he wrote for the Institute of Advanced Study. This is another recent preprint that has appeared by a number of co-authors on the area of formalization of mathematics that I would highly recommend. It is a very interesting discussion. Now, moving on, I want to talk about some milestones and recent advances. Most of them would be familiar to you, or they have also been, I'm sure, mentioned in other related talks at Topos Institute, but I'm going to go through them quickly. Of course, the formalization of the proof of the four-color theorem in Koch by Gontier in 2018 was a very important result, followed by the formalization of the Feit-Thompson proof of the odd-order theorem, again in Koch. Thomas Hales launched the FlySpec project in 2003 with the goal of verifying his proof of the famous Kepler conjecture, the sphere packing problem. So it was submitted in 1998. It was finally published in 2005, and still the reviewers said that they were not 100% sure of the proof. Of course, this is a scandal in mathematics. So Hales decided to launch the FlySpec project to verify the proof using Hall-Light and Isabel Hall. And the project was eventually completed in 2014. Then I can mention the formalization of Getter's incompleteness theorems by Paulson and Isabel Hall. The formalization of an irrationality proof of, so an evaluation of the Riemann zeta function in Koch by Mahboubi and her team. A verification of the Lorentz attractor, the verification that the Lorentz attractor is chaotic by Imler in 2015. The formalization of Scholz's perfectoid spaces in Lean by Bazard, Komelind, and Massot in 2019. In 2020, a team led by Bazard formalized Grothendieck schemes in Lean. Slightly later, my colleagues formalized it independently in Isabel Hall. Just to say that perfectoid spaces, they only formalize the definition, but the definition is extremely complicated. There is a substantial amount of material in analytic number theory by Manuel Eber in Isabel Hall. The independence of the continuum hypothesis was formalized by Hahn and Van Doorn in Lean in 2021, and slightly later independently in Isabel Zedev by a different team. So I have to say Isabel Zedev is a different version of Isabel Hall, which is based on Zermelo-Frankel set theory instead of higher order logic. A very important paper by Ellenberg and Giswit that appeared in 2017 in Annals of Mathematics, the solution to the cupset problem. So the paper was published in 2017, and the formalization in Lean was completed in 2019, only 2 years later, and was done by Damenholz and Lewis in the proof-assistant Lean. The Moretti's regularity lemma, this is an important result in extremal graph theory. It roughly says the vertices of every large enough graph can be partitioned into a bounded number of parts so that the edges between different parts behave in an almost random way. So this was used to prove Roth's theorem on arithmetic progressions that tells us that in subsets of naturals that are sufficiently big in a certain sense, we can always find a three-term arithmetic progression. So these results were formalized in Isabel Hall by my colleagues and me, by Chelsea Edmonds and Paulson, and independently at the same time they were formalized in Lean by Dillis and Meta. So we were not aware that someone was formalizing it in Lean at the same time. We were half through our project when we found out. I want to mention this project because it is really impressive that a group of undergraduate students, so I'm talking now about Matijasevic's proof of the TPRM theorem. It is really impressive that a group of undergraduate students from Bremer, they decided to self-organize and formalize this famous proof in Isabel Hall. So the statement says that every recursively enumerable set of natural numbers is Diophantine, and this gives a negative solution to Hilbert's 10th problem over the integers. So I remind you that Hilbert's 10th problem was asking to find a general algorithm which, for any given Diophantine equation, can decide whether the equation has a solution with all the unknowns taking integer values, right? And the solution to that is no such algorithm exists. This is the theorem, and I'm referring now to their AFP entry, which appeared recently, and this gained considerable publicity. So it was, I think they won some student awards as well in Germany. I find it really impressive that undergraduates are now self-organizing to prove theorems by themselves. So here in this paper, they tell the story of how they decided to do it and how they did it. The idea started in 2017, when Yuri Matijasevich gave a talk in their university. Of course, the liquid tensor experiment, Johan Kommelin talked about that a lot. Just briefly mentioning that condensed mathematics is a theory by Clausen and Scholze. Scholze is a Fields medalist. It's a theory introducing condensed sets, which is an alternative notion to topological spaces. Now, in late 2020, Scholze posted a challenge. He posted a challenge online to the Xena project blog. It's one of the Lean community blogs. So he said that he had doubts about one of his results, and nobody was able to actually check this result and verify that it's correct using pen and paper. So he challenged the formalization community to see if they can verify the results in Proof Assistant. The Lean Prover community took up the challenge, so a huge collaborative effort was launched by Comelin and many more collaborators, and they succeeded to complete the proof in the summer of 2022. And Scholze had been reporting on the progress in subsequent Xena blog posts, and this is a part from one of Scholze's posts from 2021. And he says that here we have witnessed an experiment where the proof assistant has actually assisted in understanding the proof. And this is because, as he explains, and as I mentioned before, and as of course Comelin explained in detail in his past talk, the proof assistant helped with keeping track of all the information of the proof and how every part of the proof fits in with everything else. So it's an excellent bookkeeping tool. Of course, this project gained extensive publicity. There is here an article in Nature from 2021. There was also an article in Quanta. So it looks like that we are now moving towards a new era in mathematics. So we can see a big shift already in the sense that formalization was until recently an area of computer science, but now it's quickly attracting the interest of working mathematicians, mathematics students. There are enthusiastic online communities emerging. Online tools like Zulip Chat, they enable massive collaborative projects. People meet online and they discuss and they contribute together to these big projects. Libraries of formal proofs are expanding at an increasingly high pace day by day, literally. There are student-run projects emerging, and of course, everyone is more than welcome to join. Some indications that things are shifting. In 2020, the mathematics subject classification for the first time included subject classes on the formalization of mathematics using proof assistants. And this is a big deal because now formalization is recognized as an area of mathematics, not only computer science. And Kevin Buzzard and Georges Pontier, they were both invited speakers at the 2022 International Congress of Mathematicians to talk about the formalization of mathematics. And this means that formalization is now gaining a lot of popularity among mathematicians. I just want to mention also the Hoskinson Center for Formal Mathematics at Carnegie Mellon University that started in 2021, but Jeremy Avigat talked about it in his talk already at Topos. Now, what are the main obstacles when it comes to formalizing mathematics? We need better automation. We need better automation to provide proofs for intermediate proof steps. So, of course, proofs are analyzed in an extremely high level of detail, and this can be excruciating sometimes. So it is useful to have better automation to fill in some of the intermediate steps. Then we need efficient search features because these libraries are growing extremely fast. So we need an efficient way to search through them and find what we need while in the process of formalizing. Related to that, of course, we need an efficient organization and management of the libraries of formal proofs. And another very difficult and very important search question is the interoperability of proof systems. So the possibility to translate proofs between different proof assistants. So this is one of the goals of the Didactis system, which is now in progress. And it is one of the goals of the EuroProofNet cost action. It's a big European collaborative project that I'm involved in. I will soon be the leader of the, from November on, I will be leading the working group on libraries of formal proofs. And this is one of the important problems that we want to solve, not completely solve, but let's say approach, because it's a very big and difficult problem. with all the different type systems and underlying logical formalisms that the various proof assistants are built on. So I have to say that proof assistants and foundations are, of course, only one side of the story, because progress seems to require the combination of alternative approaches, namely AI methods, machine learning methods. So an interesting analogy due to Georg Gottlob that I really like, and I want to share with you, is that he says that rule knowledge and logical reasoning versus machine learning, like neural networks, it can be seen as left part of the brain versus right part of the brain. So they say that the left part of the brain has to do with rationality and rules and logic, while the right part of the brain has to do with imagination and creativity. And the same way that different parts of the brain work together, they have different but complementary functions. We need to combine symbolic methods with machine learning and AI. And indeed, right now, the communities of machine learning and formal verification have been growing increasingly close during the past few years. There is a series of very successful conferences in this area, applications of machine learning and AI to theorem proving. There's AITP, GIG, Math AI, and many more. So we are optimistic that new advances in artificial intelligence and machine learning, they can promise novel developments in mathematical practice. And this is because pattern recognition tools for machine learning, they can find applications in searching the libraries of formal proofs. So this is already the problem with search that I mentioned before, but there is more to that. They can also recognize proof patterns. And for this reason, they can also provide proof recommendation methods, thus enhancing automation, which is the other problem I mentioned. I would like to mention this really impressive AI project. Some of my colleagues were involved in that, auto-formalization with large language models that gained some publicity in New Scientist. It is a project where so the tool developed by my colleagues, they give an input in natural mathematical language, and the output is a formalization of the statement in Isabel, and it's really impressive. The examples I've seen, it works in an impressive way. This other example that I want to mention that is not related to proof assistance, but I'm mentioning it because it's demonstrating the pattern matching efficiency of AI to assist research mathematics, is this work by DeepMind and Oxford University, where they have some new results with the help of AI. It helped them, it helped the team detect certain patterns in knot theory, therefore introducing new conjectures. So this is just to demonstrate the power of AI to assist research mathematics, thanks to its pattern matching approaches. This project had nothing to do with theorem proving. I have to clarify it once again. A few words about Isabel. So this is the proof assistant I work with. This is Isabel's webpage. You can, this is the address. That's what you're going to see if you click on it. You can download it. It's very easy to install and play with. You can find all the manuals and documentation there. These are the Isabel libraries. So if you click, for example, on the analysis library, this is what you're getting. There is a huge list of theories, of course. If you click on the theory dependencies, you're going to see the dependency graph, which is again, that's just the beginning, starting from bottom, but you get the idea. So we can also see how these theories interact with each other. I'm just showing you an example just to see how Isabel looks like as a language. So this is a lemma from the theory Weierstrass theorems from the analysis library. And it says that every polynomial function has a vector derivative everywhere for all x. Okay, and this is how the proof looks like. So you can see that proof blocks make understanding of the proof better, and the language is quite user-friendly. So Ether is quite user-friendly. It is the language Ether that I'm sure you would agree that it's not more difficult to understand than LaTeX, for instance. While, for example, Whole is much more difficult to understand when you see the code. Now, the archive of formal proofs is a vast collection of material. The libraries contain more fundamental material. The archive of formal proofs contain more advanced material. It is in different areas in mathematics, computer science, and logic. It started in 2004, and you can see the growth through the years. Right now, we have 709 number of entries, and it's constantly growing. You can check out the web page. Yeah, I just didn't mention before that Isabel Hall, I think I skipped a slide. It's based on higher order logic. I talked about Ether that produces structured, easy to read proofs, and I wanted to mention that it features very efficient automation. So we have sledgehammer and counter example finding tools like nitpick and quick check. So I already showed you these snapshots. Now about the ALEXANDRIA Project at Cambridge, which is the project I'm working in. Our goals are the following. We want to expand the body of formalized material on the archive of formal proofs and the Isabel libraries. We are working on different case studies to explore the limits of formalization, in particular in simple type theory, as Isabel is based on simple type theory. We are working on tools for managing large bodies of formal mathematical knowledge, we're working on intelligent search and computer-aided knowledge discovery. And also we're working on automated and semi-automated environments and tools to aid working mathematicians. So this is the project is funded by the European Research Council. Professor Paulson is the PI, and we are 4 postdocs working in this project. And of course, we have many external collaborators and several interns from time to time. Now, I want to start with this first project I worked on. So that was the first project I started because I wanted to start it with something down to earth. I wanted to formalize research papers. So not something from a book, but something from a research paper, which is not too complicated. So I chose a number of irrationality and transcendence criteria for infinite series. So these criteria that tell us that under certain conditions, an infinite series converges to a transcendental number or to an irrational number. So this was an original paper by Hansel, and this was an original paper by Hansel and Ruki. And with my colleague Wenda Lee, we formalized some of the theorems from these papers. Then we also continued, and I chose a paper by Erdos and Strauss, again giving irrationality criteria for infinite series, giving different criteria, testing that the limit of a series would be an irrational number, under which conditions this happens. So all this has been formalized. These are our AFP entries, and this is our paper that appeared in Experimental Mathematics. So for that, it was a first case study, as I mentioned. We found out that we needed to develop some background material on infinite products, which was done by Paulson. And an interesting comment that I want to mention regarding this project is for the second paper that we formalized. For some of the results, we had to assume Roth's theorem on rational approximations as a given, which is a very big famous theorem by Fields metallist Roth, which has not been formalized. So we assumed this big theorem as a given, and then we formalized the theorems following from that as corollaries. This second project involving formalizing ordinal partition relations in Isabel Hall. It was done by, this was a project I was involved in together with Mina Jamonji, who is a leading set theorist, and Lawrence Paulson, my PI, again appeared in experimental mathematics. This was a formalization in infinity combinatorics of a number of, a formalization in Isabel Hall, sorry, of results in infinity combinatorics and set theory by Erdős, Milner, Baker, Larson, and Nash-Williams, a number of authors, and they were all leading to Larson's proof of an unpublished result by Milner, so about ordinal partitions. So these are the AFP entries associated with this work. Larry Paulson talked in detail about this project in his talk at the Topos Institute Colloquium. So this shows that actually simple type theory, Isabel Hall, can be used in formalizing results in this area. So it is interesting that it was done in Isabel Hall and not in Isabel ZF, which is an alternative version of Isabel. And this is thanks to this entry by Paulson, where he formalized the Mello-Frankel set theory in higher order logic. I already mentioned this big project as well with my colleagues, Chelsea Edmonds, who is a PhD student of Larry Paulson, and Larry Paulson, the formalization of the Meredith regularity lemma and Roth's theorem on arithmetic progressions. I mentioned before, this is a fundamental result in extremal graph theory, and Roth's theorem on arithmetic progressions is a big result in combinatorics number theory, attesting that we can always find three-term arithmetic progressions in subsets of the natural that are big enough in a certain sense, simultaneously independently formalized by Dillis and Metainling. So these are our AFP entries, if you want to have a look in our code. And this is the associated paper. This work by my colleagues, Anthony and Wenda, together with Larry Paulson, this was a case study to check the limitations of simple type theory. So there was a challenge posed in some sense by the Lean community. So schemes had been independently formalized in Lean, but it was believed that, there was a doubt regarding whether it is possible to formalize results of this nature in simple type theory. But apparently, thanks to Andoni's and Larry's and Wenda's work, it is possible. So this shows that simple type theory is powerful enough. This is their paper and their AFP entry. Along the same lines, so in the same spirit of demonstrating the expressiveness of simple type theory, Anthony and his intern over the summer, Andrea and Donna Matteo, they formalized some material in higher category theory, again, to explore the limitations of simple type theory and the expressiveness of it. So this is a submitted preprint and an upcoming AFP entry. Now, another big project I'm involved in, I had the initiative to start this, this line of formalization work, is additive combinatorics. So we started with formalizing some central theorems about the structure and the structure of subsets of infinite subsets of abelian groups. So these are results about their cardinality and structure. For example, we formalized the Blunecke-Rousset inequality with Larry Paulson and Skovansky's theorem. Again, I formalized this with Larry Paulson, and our source was the course by Timothy Gowers for the University of Cambridge, Introduction to Additive Combinatorics. So I have built on this work recently with my intern Mandas Baksis from the mathematics department over the summer. And we formalized Kneser's theorem and the Cauchy-Davenport theorem. Again, these are results giving information about the cardinality of some sets of infinite subsets of finite subsets. I said infinite. So the objects we study here are some sets of finite subsets of abelian groups, and we have results on their cardinality under certain conditions. It is interesting that we formalized Kneser's theorem following a paper from 2014. This is a much older result, but we followed a research paper from 2014 on a similar short proof of this result. It is an upcoming AFP entry. And this is another big project that we're very proud of. So with my intern Mandas Paxis and Chelsea Edmonds, who is Larry Paulson's PhD student, we recently formalized the Balog-Zemuredi-Gowers theorem in Isabel Hall. This is a profound result in additive combinatorics from 2001 by Gowers. It played a central role in Gowers' proof deriving the first effective bounds for Zemuredi's theorem. Zemuredi's theorem is a generalized version of Roth's theorem for arithmetic progressions. So Roth's theorem talks about arithmetic progressions of length 3. Zemuredi's theorem is for arithmetic progressions for any length, for arithmetic progressions of k terms. Something very interesting about this proof is that it involves an interplay between graph theory, probability theory, additive combinatorics involving algebraic objects, and this interplay is expressed by an implementation of locales, which is Isabel's module system. So for that, we made use of a new general undirected graph theory, undirected graph theory library developed by Edmonds. It is general in the sense that it doesn't have restrictions on types. For example, we wanted to define copies of we wanted to define a finite abelian groups that are copies of certain subsets of vertices of a graph. And in other libraries, when the vertices of a graph are represented as natural numbers, we will not do that anymore because we're working with abelian groups and we have a more general type. But this more general undirected graph theory library helps us to do so. Again, we followed Gowers' notes for the course in additive combinatorics for 2012 for the mathematics tripos. The AFP entry will appear soon. Some other projects by my colleagues. So elements of differential geometry in Lean, this time by Anthony Borg and his intern Niccolo Cavalieri. Also, Anthony worked on a quantum computation library with his interns Hannah Lachnit and Jihun He. These are the references, the paper, and the corresponding AFP entry for his library on quantum computation. This project by Larry Paulson, he formalized an undecidable problem linked to the continuum hypothesis. So it is a proof by Erdos, actually, and it's showing that if the continuum hypothesis fails, then every family of analytic functions satisfying the Wechsel property, certain property about analytic functions, had to be countable. But if the continuum hypothesis holds, then there exists an uncountable family satisfying the Wechsel property. So this undecidability result was formalized by Paulson, and you can see here the corresponding AFP entry. There is a paper as well. My MPhil student, Niels Lohrmann, formalized Durand's graph theorem. It's a very important result in extremal graph theory. It says that we can bounce the number of edges that can be included in an undirected graph that does not have a complete subgraph of a given size. And of course, we have much more material on the archive of formal proofs, even more AFP entries. I'm going through them quickly. I have compiled a list here. So there's material in combinatorics, set theory, commutability theory, irrationality results, analysis, geometry by Wenda and his student, more combinatorics. This is a project I did in 2020. I formalized quite a few results about amicable numbers. I formalized a lot of criteria like Tabit ibn Kurat's rule, Terile's rule, Borel's rule with breeders, Euler's rule, all these criteria for amicable numbers. Fourier series by Paulson. Another little project that I'm really fond of, I formalized Aristotle's esoteric syllogistic in Isabel Hall. The prime number theorem by Ebert and Paulson. I suggested to Larry Paulson to formalize the theory of quaternions, and then I expanded on that and I formalized the theory of octonions in Isabel Hall. That was in 2018. And some more results in analysis, Green's theorem, some more results in algebra by Anthony Borg, and projective geometry by Borg, and some work in counting the number of complex roots and winding numbers, the Boud and Fourier theorem by my colleague Wenda Lee, who has a lot of work verifying tools for computer algebra in Isabel Hall. And I mentioned before that CERT is a very big part of what we're hoping to do. It's a very big part of the current problems for modern proof assistance. So that's one of the things we're trying to solve. So together with my colleague Yanos Stathopoulos, who is an expert in natural language processing, we developed a search engine for the Isabel libraries and for the AFP. So what is interesting about this search engine, this is the snapshot of the web page. You can find this at this address online, and you're free to play with. The manual is online, and we have some videos on YouTube to explain how it works. So it is interesting that it is concept oriented in the sense that, for example, a user cannot know in advance how to search for a certain object, because we cannot know how it is written in the library. For example, if we're looking for cosine, it can be written as cos. And then if we search for cosine, then pattern matching doesn't work and we cannot find the result. But with concept-oriented search, this problem is resolved because it associates the concept we give with many associated other notions and searches through the entire library and the entire AFP. Of course, we also have pattern matching search using keywords, but concept-oriented search is a very big part of how it works. We can, yes, sorry.
Sorry, Angeliki, to interrupt. If you could just move to wrap up in the next 5 or so minutes. Yeah, sorry, thanks.
Yes, I'm finishing, yes. So you can filter your whether you can search in the AFP or in the libraries, and you can choose definitions or other facts. You can exclude theories if you find theories that are not related to what you're searching for. And contrary to find theorems that only searches results in the theorems you have loaded in your active session, this tool can search everywhere. And this is really important because it is not easy to know how the library has been organized. Of course, organizing a library of mathematical knowledge is a highly non-trivial task. There can be many different alternative ways to do that. So this helps the user with finding what they're looking for. So yes, you can try out the videos by yourself. I would invite you to try it out after watching our videos. explain how it works, and because we would really like to have some user feedback, which you can give via interface as well. There are instructions about that. And to finish, I'm going to quickly talk about some contributions by members of the ALEXANDRIA Project in AI and machine learning tools. So my colleague Wenda Lee has been involved in many of these projects. So in this paper, the defined task for the model was to fill in missing intermediate steps in a proof. And this involved a study of the reasoning capabilities of neural sequence-to-sequence models. Then this work, where they developed a pre-training methodology involving only fundamental reasoning biases with no underlying mathematical knowledge. This work, LISA, language models of Isabel proofs. My colleagues developed a collection of parallel natural language and Isabel Hall proofs, and they created so they built language models on this large corpus of Isabel proofs from the archive of formal proofs. This new work, Thor, that is going to appear in 2022, it is a very powerful tool developed by a group of my colleagues that involves a combination of automated theorem provers like Sledgehammer with integrated language model, and the combination of these two proves to be extremely powerful in finding proofs. So it is combining the best of both worlds, and it has considerably improved performance. It's a very hopeful contribution of AI to theorem proving. Then I already mentioned this project, auto-formalization with large language models. I mentioned this before. You enter a proof in natural language, and then you get a proof formalized in Isabel Hall. It's extremely impressive. Finally, this work by my colleague Yanos Stathopoulos, together with Anthony Borg and Lawrence Paulson, they built a collection of parallel natural language and Isabel Hall proofs, and an annotation tool to record information about these artifacts. So, of course, this collection could be used for many reasons, and it's actually connected to the Serapis search engine. I just have to say that Serapis stands for, our search engine, it stands for it stands for Search Engine by the ALEXANDRIA Project for Isabel. And I didn't mention the joke that it's actually an intended pun. We chose the name Serapis because Serapis was a god worshipped in Alexandria, Egypt. And since our project is named Alexandria, we thought it would be appropriate whenever we have a problem looking for specific facts, and we are in trouble. So of course we resort to Serapis, right? So it's just a pun, but it stands for Search Engine by the ALEXANDRIA Project for Isabel. So to conclude on the machine learning and AI side, I'm going to mention this paper of mine where I have a quite bold, I must say, research suggestion. And at the moment it's quite speculative, but my suggestion is to use machine learning to extract computational content of formal proofs based on extensive formal libraries of simple proofs, which would have been formalized with a computational content made explicit. So I'm suggesting to build a library of formal proofs with explicit computational content, and then a machine learning tool would feed on this information and provide computational content for more complicated proofs. This is in this paper that I'm stating here. And with this, I think I'm finishing. So thank you very much.
Thanks very much. Okay, so yeah, maybe we have time for a quick question or two if anyone in the audience wants to go ahead and just ask.
Yeah. Hi, Angeliki. I have lots of questions for you. Yeah. Thank you very much.
We can also talk more.
after the thing finished, right? But I think after we normally stop the recording and then have a little bit more of conversation if you have a few more minutes. But I think my main question is about this problem, this big problem that you mentioned of interoperability of theorem provers, because as we were saying, kind of, it seems a little bit silly to be having teams competing to formalize the same result when we know that there's loads of other stuff that have not been formalized. And hence I kind of wondered if, if you have on your mind already some sort of difference, cons and pros of each one of the different provers for someone who is new to this area or not, kind of.
Okay, so of course I cannot be completely objective because I've only worked with Isabel, right? And I don't have any experience with Koch or Lin, I have to say. But people who work with Lin and then they try out Isabel, so some of my students, for example, they are very impressed with Isabel's automation. So it is a very big plus that we don't have in other proof assistants. I said before that the easier language is very easy to understand, it's user-friendly, but automation is a very big thing. Also, when it comes to search, I'm very happy with our new search engine. It's very useful and practical for now, so far. I mean, opinions vary. I gave a reference before where I gave a reference on
Question answers, yeah, I saw that. That looks
on an interview article with 11 experts, and they talk about different formal systems and their pros and cons. So I also mentioned the work by Anthony, Wenda, and Paulson, where they formalize some results, routing schemes that people were not expecting that simple type theory would be powerful enough to formalize these results, but they were wrong. So it was possible. So simple type theory can be very powerful. It is largely a matter of taste. Now, I agree that it looks like a bit of a waste of time when people give so much of their time and work to formalize things in different proof assistants. The same theorem in different proof assistants. But I wouldn't say it's a waste of time because we learn a lot through this process. It's a work in progress. So unfortunately, right now, interoperability doesn't work. So it is one of the goals for the future. I mentioned the didactic system, which is being developed at the moment. It will be an intermediate system, so there will be proofs translated from other systems to didactic, and then
yeah, we are going to have another talk from Gilles Dawek, who is one of the main creators of Deducti. So I'm keeping my other questions for him too. But yes, it is as you say, it is difficult. It is a difficult thing. So kind of, I thought because of your question and answer to all these guys, you would have some more. I mean, of course, I know that the AFP is very big. And I know that there's more automatization tools for Isabel, but yes, I guess thanks for saying that is still up for grabs, right? Kind of.
Yes, but yes, interoperability is a huge problem right now, and there is no obvious easy solution. I mean, we expect to have partial solutions, but not a global solution because there are so many obstacles because of the different type systems of different underlying logical systems of every proof assistant. It's very hard. It's a very hard research question at the moment.
So I think since we're 5 minutes past the hour, we can switch to the open discussion session, and anyone who wants to can stick around and chat. So let's thank the speaker again. Okay, so yeah, so the live stream